A-Level Mechanics, Simple Harmonic Motion Part 1. This video shows how simple harmonic motion occurs. Let's have a look at simple harmonic motion. Consider a particle of mass m suspended on the end of an elastic spring. While it hangs at rest, the position of the weight is called the equilibrium position. If it's pulled down and released, it'll oscillate up and down. It'll rise above the equilibrium position by the same amount it descends below the equilibrium position. The particle generates a sine curve. As the mass moves up and down, we can construct a graph to show its motion. The distance it moves up and down is called the amplitude of the motion and is represented by the letter A. The motion then repeats itself over and over again. The number of times it does this each second is called the frequency, represented by the letter nu. The unit of frequency is called the hertz. 1 hertz is 1 cycle per second. If A and B are 2 points 1 second apart on the graph, then we can see there are 4 cycles between A and B, and so the frequency nu is equal to 4 hertz. If t is the time the mass takes to complete 1 cycle of the motion, then t is called the time period. On the graph we have t is equal to 1/4 of a second. So we can see t is equal to 1 over nu. The time period is 1 over the frequency. If we also consider the motion of a tuning fork, the pendulum of a clock, ripples on water, or the string of a guitar, they all move back and forth or up and down with a regular pattern. These also form sine curves. Let's see how the simple harmonic motion equation is derived. Consider a mass m resting on a smooth horizontal plane attached to a wall with a spring of stiffness k. Then the mass will rest in equilibrium when the spring is at its natural length. Suppose the string is stretched by an amount s and then released. We can draw a diagram showing the spring stretched by an amount x. We can now draw in the forces acting on the mass m. There'll be a weight mg acting vertically down. There'll be a normal reaction n acting vertically up. And there'll be the tension in the spring. Now let the mass have an acceleration of a. Our extension x is measured to the right, so that's our positive direction. Which means that when resolving horizontally using F equals ma, the force is minus t. So minus t equals ma. But we know the tension is equal to the stiffness times the extension, so t is equal to kx. And a can be written as d2x by dt squared. So we have minus kx equals m into d2x by dt squared, which we can rearrange as d2x by dt squared equals minus k over mx. Now k and m are both positive numbers, so we can write k over m as omega squared. Now this gives us the equation d2x by dt squared is equal to minus omega squared x. And this is the fundamental equation for simple harmonic motion. So, for simple harmonic motion, the acceleration of the body is proportional to the distance of the body from the equilibrium position, and it's towards the equilibrium position. Any body obeying this equation is said to be moving with simple harmonic motion. we have derived the simple harmonic motion equation, which is d2x dt squared is equal to minus omega squared x. Now we need to solve this. Well, to solve it, we're going to use a trick. We have dx by dt is equal to v. So if we differentiate again, we get d2x by dt squared is equal to dv by dt. Then we can use the chain rule to say d2x by dt squared is equal to dv by dx times dx by dt. The dx's would cancel. And dx by dt is equal to v. So d2x by dt squared is equal to dv by dx times v, or d2x by dt squared is equal to v dv dx. This is a very useful formula and can be used in all sorts of situations. So the simple harmonic motion equation becomes v dv dx equals minus omega squared x. And we can separate the variables by multiplying both sides by dx and then integrating. And that gives us the integral of v dv equals minus the integral of omega squared x dx. Now if we integrate v dv, we get v squared over 2. And if we integrate minus omega squared x, we get minus omega squared x squared over 2. But we must remember to add a constant, plus c. Now we can double both sides to get v squared equals minus omega squared x squared plus 2c. And if a is the maximum extension, then when x is equal to a, we have v is equal to 0. So 0 squared equals minus omega squared a squared plus 2c. In other words, 2c is equal to omega squared a squared. So substituting that in for 2c in equation 1, we get v squared equals minus omega squared x squared plus omega squared a squared. And that means we get v squared is equal to omega squared into a squared minus x squared. And if we take the square root of both sides, that gives v equals plus or minus omega into the square root of a squared minus x squared. And so the speed of the particle at any time is equal to omega into the square root of a squared minus x squared. Now this is a very important result. You don't necessarily need to know how it was derived, but you should remember it. It's very useful when solving problems. Let's have a look at an example. Example 1. If v is equal to 10 meters per second when x is 0, find v when x is equal to a half the amplitude. Well, to solve this, we've got v is equal to 10 when x equals 0. So v squared equals omega squared into a squared minus x squared. And this gives us 10 squared is equal to omega squared into a squared minus 0 squared, or omega squared a squared is equal to 100. Now if x is equal to half a, then v squared is equal to omega squared into a squared minus a quarter a squared, or v squared is 3/4 omega squared a squared, which is equal to 3/4 times 100, or 75. If we take the square root, we get v is equal to plus or minus the square root of 75, which is equal to plus or minus 8.66 meters per second. Now let's see how we can solve the equations to find the displacement at any time. We want to find x in terms of t, and we've got dx by dt is equal to plus or minus omega into the square root of a squared minus x squared. Now we can separate the variables by multiplying both sides by dt and dividing both sides by the square root of a squared minus x squared. And then we can integrate. And that gives us the integral of dx over the square root of a squared minus x squared is equal to plus or minus omega times the integral of dt. Now to integrate the left-hand side, we've got the integral of dx over the square root of a squared minus x squared, and we can make the substitution x is equal to a sine theta, which means dx by d theta is equal to a cos theta, or dx equals a cos theta d theta. Now, if we substitute that into the equation, we have the integral of, and on the top we've got a cos theta d theta, on the bottom we've got the square root of a squared minus a squared sine squared theta. Now on the bottom we can factorise out the a squareds and take them outside the square root sign. So that gives us a into the root of 1 minus sine squared theta. Now the a's cancel top and bottom, and the square root of 1 minus sine squared theta can be written as the square root of cos squared theta, which leaves us with the integral of cos theta d theta over cos theta. And the cos thetas cancel, and we're just left with the integral of d theta, which when we integrate it is simply theta. Now theta is the inverse sine of x over a. So now we're left with the inverse sine of x over a is equal to plus or minus omega times the integral of dt. Now the integral of dt is simply t, so we have the inverse sine of x over a is equal to plus or minus omega t plus of course a constant which we'll call epsilon. So x over a is equal to the sine of plus or minus omega t plus epsilon. Now we don't need to have plus or minus omega t, because the sine of minus omega t plus pi is equal to the sine of plus omega t. And since epsilon is arbitrary, we don't need to worry about the plus pi. And that leaves us with x is equal to a sine omega t plus epsilon. This is another important equation you should remember. You don't need to know how it was derived, but you should remember the result. So we see the displacement is a sine curve with magnitude a shifted on the x-axis by an amount minus epsilon over omega. Let's have a look at an example. Draw the graph of x equals 1.5 sine 2t plus 1.2. Well, if we draw the graph, we see it is a sine curve. We see that the height of the sine curve is 1.5, and we see the sine curve has been shifted by an amount minus epsilon over omega, which is minus 1.2 over 2, or minus 0.6. The sine curve normally goes through the origin, but now it's going through the point minus 0.6 on the x-axis. So far we have three equations involving simple harmonic motion. d2x by dt squared equals minus omega squared x is the fundamental formula for simple harmonic motion. We can solve this to find v in terms of x. We have v squared equals omega squared into a squared minus x squared. And we can also derive the formula x equals a sine omega t plus epsilon. X is the displacement from the equilibrium position and a is the maximum displacement. From equation 1 we can see the acceleration is proportional to the displacement x and is always back towards the equilibrium position. So, if the particle is at the equilibrium position, x equals 0, then the acceleration is 0. The second equation says the maximum speed is equal to a omega, and that's when the object passes through the equilibrium position. Now from equation 3 we can work out the time period. The cycle repeats when omega t plus epsilon increases by 2 pi. Let capital T represent the time period. So if the time small t increases by the time period capital T, then omega t plus epsilon increases by 2 pi. Well, if we remove the brackets, we get omega t plus omega times the time period plus epsilon equals omega t plus epsilon plus 2 pi. Then we can cancel omega t and epsilon from both sides to get omega times the time period t equals 2 pi. This gives us that the time period t is equal to 2 pi over omega. And we also know the frequency nu is equal to 1 over t, that is 1 over the time period. In example 3 we're told an object moves in simple harmonic motion. starting at the equilibrium position, with an amplitude of 30 centimeters and a frequency of 100 Hz. In part 1, we're asked to find its maximum speed. Well, to solve this, we know the frequency nu is equal to 100 Hz. So that means the time period t is 1 over 100, and omega is 2 pi over the time period t. So it's equal to 2 pi divided by 1 over 100, which is 200 pi. Now the maximum speed is a omega, where a is the amplitude in meters. So that's 0.3 times 200 pi, which is equal to 188.495. So we have a maximum speed of 188.5 meters per second. Now in part 2, we're asked to find its speed when it's 20 centimeters from the equilibrium position. Well, in this case, we can use the equation v squared equals omega squared into a squared minus x squared, with x equal to 0.2 and a equal to 0.3. So v squared is 200 pi all squared times 0.3 squared minus 0.2 squared. Well, 0.3 squared minus 0.2 squared is 0.09 minus 0.04, which is 0.05. And so we have v is equal to 200 pi times the square root of 0.05, which works out to be 140.496. So the speed is 140.5 meters per second. Now in part 3, we're asked to find its displacement after 1/3 of a second. Now since it starts at the equilibrium position, epsilon will be 0. The sine curve starts at the origin. And so the equation becomes x equals a sine omega t, with t equal to 1/3 of a second. So x is equal to 0.3 sine 200 pi times a third. And we've got to remember that we must have our calculator in radians to get x is equal to 0.2598 meters. So the displacement after 1/3 of a second is 26.0 centimeters. Let's have a look at one last example, example 4. A mass of 0.3 kilograms is suspended from a point O by an elastic string of length 1.2 meters and modulus 15 newtons. It is held 1.3 meters below O and then released. Now in this question we're told to take g as 10 meters per second squared. And in part 1 we're asked to find its equilibrium position. Now to solve this, we need to draw a diagram. It must show the mass resting in equilibrium. So let the extension be E. That is the distance below the natural length. Then we can mark in the forces, and we've got a weight acting vertically downwards of 0.5 g, and a tension acting vertically upwards, we can call that T. Then we can resolve vertically. We get T is equal to 0.5 g, and since we're taking g as 10, that gives us T is equal to 5 newtons. Then we can use Hooke's law. T is equal to lambda x over L. Now we know the tension T is 5, we know lambda is equal to 15, and the natural length is 1.2. So 5 is equal to 15e over 1.2, which we can rearrange to get E is equal to 6 over 15, or 0.4. So the equilibrium position is 0.4 meters below the natural length, which means the equilibrium position is 1.6 meters below O. Now in part 2 we're asked to find the amplitude of each oscillation. Now the mass is released from 1.3 meters below O, and the equilibrium position is 1.6 meters below O, which means the mass travels a distance of 0.3 meters from its position at rest to the equilibrium position. So that tells us the amplitude is 0.3 meters. Now in part 3 we're asked to find the fundamental equation of motion of the mass. Now again we need to draw a diagram. Now the important thing to remember is the displacement x must be measured from the equilibrium position. Now the equilibrium position is 0.4 below the natural length. So when we draw the diagram with displacement x, the extension will be x plus 0.4. Now we can mark in the forces and resolve vertically using F equals ma. There's the weight of the object again, which is 0.5 g. And there's the tension. We can call this tension T. We can mark in the acceleration a, and because the extension is drawn downwards, we have the positive direction for a is down. And so we have the force down is 0.5 g minus t, and that's equal to 0.5 a. So t is equal to 0.5 times 10 minus 0.5 times a, or t is equal to 5 minus 0.5 a. Now we can also use Hooke's law, which says t is equal to lambda x over L. Lambda is of course 15 and the natural length is 1.2. So t is equal to 15 into x plus 0.4 all over 1.2. Now t becomes 5 minus 0.5a, and on the left hand side 15 over 1.2 is equal to 12.5. So we have 12.5x plus 12.5 times 0.4, which is plus 5. Now we can subtract 5 from both sides and multiply both sides by minus 2. And that gives us a is equal to minus 25x. Now we know a is equal to minus omega squared x, so from that we have omega is equal to 5. So the fundamental equation is d2x by dt squared is equal to minus 25x. Now in part 4 we're asked to find the time period of one oscillation. Well, we know the time period is 2 pi over omega, so that's 2 pi over 5, which is equal to 1.2566. So we have the time period is 1.26 seconds. Now in part 5 we want to find its distance below O after 1 second. So we need to find its displacement at any given time. So using x equals a sine omega t plus epsilon, we have, when t is equal to 0, the mass is 0.3 meters above the equilibrium position, so x is equal to minus 0.3. But a is equal to 0.3 and omega is equal to 5. So we have minus 0.3 equals 0.3 sine 0 plus epsilon, because t is 0. So that gives us minus 1 is equal to sine of epsilon, so epsilon is 3 pi over 2. So the equation is x equals 0.3 sine 5t plus 3 pi over 2. Now when t is equal to 1, x is equal to 0.3 sine 5 times 1 plus 3 pi over 2, which is equal to minus 0.08509. So if we take that away from 1.6, we get the distance below O is equal to 1.515 meters.